This is my home lab. Here I have a Raspberry 3 connected to a DHT11 which measures temperature and humidity. It's also connected to a relay that acts as a switch for the alarm flash. On this Pi 3 there are three things running: a program that reads the sensor data and sends it to a MQTT queue, another program that waits an event and triggers the alarm, and finally a server that runs edge workers with mini flare inside the Raspberry Pi. The Pi that is connected to my home lab is attached to this service through an orchestrator that allows submitting new code to run on these edge workers remotely. At the moment I have this function running that receives sensor data and saves them in a time series database. This database has historical data that the sensor has measured over time. What we want is to create a predictive model that can, based on historical data, estimate what temperature we should have at this moment, and if they diverge a lot, then we have an anomaly and we have to activate the alarm. To do this, we start by creating a data snapshot. A snapshot is a file of data that has been prepared to be trained by a model and can be used to make comparisons between models. In this case, we're going to make a snapshot of forecast data that will predict the future temperature that we should have. Let's read the data from the time series database that we've been using in the worker. Let's use the first of the metrics, which is the temperature, and give it that name. Let's create a window of 20 past samples for each forecast and predict one temperature ahead. And let's ask for this segmentation normalization of the data. Next, let's create our project to train our predictive model. Let's name it Predict Home Lab Temperature and store the result on this bucket. Let's describe the structure of the model. First, it should receive a time series feature with the temperatures passed. And let's predict the temperature, which is a numerical value. Next, we are going to add the snapshot we just created. And we are going to ask to generate artifacts for edge workers and embedded systems. Finally, we're going to ask the system to train the model. Let's use the snapshot that we just added. And when the model is finished training, we can see the result of the training process. And here we have some information about the normalization of the snapshot we used. And in the evaluation part, we have access to evaluation information of the training process, including loss and error and the evolution through the training process. Now that we have a suitable model, we have to load it into the function code, estimate temperature, and if diverge, trigger the alarm. We have the original function here, but we are going to replace it with this one. Now the function loads the model through a bucket. Let's change the identifier to the one we just trained. And we are going to store the model on a global variable to ensure that the model is only loaded once. In addition to the model, we also store if we are in anomalous state and the time window of the last 20 sensor measurements. We continue to store the data on the time series database, and here we detect if the temperature is anomalous or not. First, we use the model to estimate the temperature we expect at this moment, and we calculate what's the maximum acceptable deviation, in this case 3 sigma, that is 3 standard deviations from the sample. If it's higher than this value, then it means that it's 99% higher than the samples that we saw in the training data. If this is true, we trigger the alarm, and we toggle it both in the inverse case. Now, the code has several dependencies, and it is necessary to compress everything in a file with Webpack. And for the sake of simplicity, let's upload the file through the command line instead of copy pasting the file in the browser. And finally, let's deploy the code in the worker that we have running on the home lab. Now that the code is running in the worker, we can simulate an anomaly like a fire. And the temperature increase triggers the alarm.